Hello, am I audible? Okay, thank you, Gautam. We will wait till 6:05. We will wait till 6:05 and after that we will start the class. You can we shall wait till 6 we shall wait till 6:05. If any one of you have any doubt, you can ask in the chat or you can unmute yourself and you can speak. Happy Independence Day, Ronak. Can any one of you confirm if my screen is visible or not? So it is 6:05 now. So I will start the class. Welcome all of you to live sessions of solid mechanics course, which is getting floated on NPTEL. It is being taken by Professor Ajit Kumar at IIT Delhi. So I am Manoj Shikhar. I am one of the TAs in this course, solid mechanics. I'm a PMRF scholar. I'm a PMRF scholar at Applied Mechanics Department, IIT Delhi. I've done my BTech and MTech from IIT Kharagpur, and I shall be taking live sessions on Tuesdays from 6 p.m. to 8 p.m. You will be having another live session by Roshan on next week, on Fridays, I guess. So first of all, I would like to wish you happy Independence Day. Now let's move on to our session today. I will start from recapitulation of what has been done in week 3 by Sir, and then we will solve some problems. If you have some doubts in between, you can unmute yourself and ask. You can also write in the chat. It's up to you, whatever you prefer. And if you have some doubts in like some numericals, which I will be dealing with, you can also ask at that time also. So let's start. Let me just fix my camera. Also, I'd like to declare one thing that you people get assignments every week. Those assignments are graded assignment, and we are not supposed to help you with those. So kindly refrain from asking any questions which are currently a part of assignment 3 or any assignment which is currently active. We are not allowed to help you with that. Those of you who want to get the notes of these NPTEL lectures, you can get it from this website. This is the website of Professor Ajit Kumar. Here you will find the notes of the video lectures for the solid mechanics course. You may have received the links of live sessions and the Google Drive link for where we store all the files we use in the live sessions. So you can access those things from that link. In week 3, 3 lectures were there, and the first lecture was on principal planes and principal stress components. Then we moved on to maximizing the shear component of traction. And after that, in lecture 9, Sir has covered Mohr circles. So in this PPT, I have included the portion of first two video lectures, and in this Mohr circle, I will do it manually. So why do we need to study principal planes? So we know that at any point in the body, we have different tractions on different planes. And each of these planes have their own normal component of traction as well as shear component of traction, which we have found out. Like for normal component, what we used to do, we first used to find T by using formula sigma into N, sigma dotted with N. And after that, we used to dot this traction vector, which we had found T with normal vector of the plane. In today, few examples will be there where we will be using this formula a lot. Now, among these planes, the planes on which the normal component of traction becomes maximum or minimum are called principal planes. So this is essentially the definition we are forcing, that the planes where our normal component of traction will become maximum or minimum, they will be called as principal plane. And the values of the normal traction on those planes, they will be denoted by principal stress components. Now, why do we need to know the principal stress components? So the reason is in one of the failure theories that predicts that when a body will fail, we require the knowledge of principal stress components. So we should study about this. Now, this is the formula for the normal component of traction on a body, and it is denoted by sigma nn. What is our objective? Our objective is to maximize or minimize this sigma nn. Now, in the like in 11th or 12th, you may have read that to maximize or minimize any quantity, we need to find the critical points, the points where the function will become a maxima or minima, or it could be a point of inflection. So sigma nn is essentially a function of coordinates here, right? Sigma depends up depends upon point only. So sigma nn is a function of coordinates. So we have to find. So while finding this principal planes, our objective will be that we already know the stress matrix representation. Like the matrix representation of this stress tensor, we already know that. And we need to find the direction cosines n1, n2, n3 of the plane. This n1, n2, n3 of the plane, so that we can find the principal plane. Now, if you convert this particular formula into the matrix form, it will look like this. You have put the stress tensor matrix, you have put the normal vector, and you are dotting it with normal vector. Now I look at one thing. Here sigma 1 to sigma 2 1 is written, but we have already proved in our lecture 6 from A and B that off diagonal elements will be equal. So we can replace sigma 2 1 by sigma 1 2, sigma 3 1 by sigma 1 3, and sigma 3 2 by sigma 2 3. If we move on to indicial notation, we can replace sigma n by this expression. This has been already covered in previous lectures. So if you have doubt in it, you can go to the previous lectures and you can look at these. Now, these components n1, n2, n3 of the normal, they are not independent of each other because they have a constraint. The constraint is that the norm of normal vector should be equal to 1. It cannot be greater than 1 or less than 1 because it is a unit vector. So we get relation n1 square plus n2 square plus n3 square minus 1 equal to 0. Suppose if you want to find n3, And if we know N1 and N2, we can use this formula to find N3. Also, one more thing is you can see here. This. So what do we need to maximize or minimize? We need to maximize or minimize this sigma NN. And with respect to what do we have to maximize or minimize? So we have to maximize or minimize this sigma NN with respect to N1, N2, N3. So from calculus, we can do the differentiation of sigma NN with respect to these, and we can find where it is becoming 0. And at those critical points, we can find the value of sigma, and that will give us if it is a maxima or a minima or if it is a point of inflection. But there is one constraint here that N1, N2, N3, they are not independent. So how do we deal with this kind of situation? We can deal with this kind of situations by using the method of Lagrange multipliers to maximize or minimize any function. So, so whenever a function is to be minimized or maximized in the presence of a constraint, we can use the Lagrange multiplier. Initially, what was our objective function? Our objective function was this sigma NN. Basically, this thing is our objective function. But we are having one constraint here. So we need to update our objective function to include that constraint. And this updated objective function is called augmented function sometimes. So here you can see our augmented function is f. It is a function of n1, n2, n3, and lambda. Lambda is actually called Lagrange multiplier. So what we have done, this is our objective function. If you look at it, this initially we had to minimize or maximize this. So this was our old objective function minus lambda into this is our constraint. I'd like to mention one thing here. The sign doesn't matter here. We could have taken plus also. It doesn't matter. So our new function which we have to maximize or minimize is this function f. And as I've already told you, this term represents our constraint. Now we will apply differential calculus here. We will differentiate this function f with respect to each of these variables. And this will give us 4 different equations. So for differentiating this f with respect to n1, we will get sigma ij because this is given already. So this will not be getting differentiated. Sigma ij will be as it is. We will first differentiate del nj with respect to del n1 and ni will be here. Then nj will be here, but now we will differentiate del ni with respect to del n1. And the same thing will happen with this part. 2 times del ni by del n1 because first we differentiated this thing, we will get del ni by del n1 plus into ni plus ni into del ni by del n1. Now this ni is a component, so this is essentially a scalar. So we can move it from here to here, here to here. That's why we were able to write it as 2 del ni by del n1. Now, now since n1, n2, and n3 they are independent of each other, we can write that del ni by del nj by our Kronecker delta ij function. It will be 1 when I equal to j and it will be 0 when I is not equal to j. So what will happen? Here in this case, del f by del n1, we will replace j by 1. So here it will be sigma ij del j1 ni plus sigma ij nj del i1 minus 2 lambda del i1 ni. Now this particular expression, it has been written for a generic n. That is, we have differentiated for nk. Hence the expression is sigma ij del jk ni plus sigma ij nj del ik minus 2 lambda del ik ni. So if you remember, what will happen? We will replace sigma ij by sigma ik because j and k, they are same because of this Kronecker delta operator. Similarly here, we will replace I by k. So we will get sigma kj nj minus 2 lambda nk. And that is what has been written here. Now we can replace this dummy index j by I because this is a dummy index. This is getting summed here. You can see j is getting summed here. So what will happen? Sigma ki ni. So what we write, we can collect these two terms together. We can write sigma ik plus sigma ki into ni minus 2 lambda nk. We will again invoke our AMB, angular momentum balance. And from there, we know that sigma ik equal to sigma ki. So what will this become? This will become 2 sigma ki ni minus 2 lambda nk equal to 0. And we can cancel the 2 part. And k will go from 1 to 3. What will happen if we differentiate f with respect to lambda? We will get our constraint equation directly. Right? So from this equation, we can see that we can write this equation in the matrix form. We can write it as sigma into n because this is essentially a product of a matrix with a vector. So we can write sigma into n, and this particular thing is a vector. So lambda into n. In mathematics, we have seen this form a lot in matrix algebra, and this is called eigenvector problem, where n is the eigenvector of sigma and lambda is the eigenvalue of sigma. Now, one of the properties of eigenvectors is that suppose if x is an eigenvector for a matrix, then a constant time x, like for example, here I have denoted it by b times x will also be a eigenvector of sigma. So if x is a eigenvector, if x is an eigenvector of A, then Bx is also an eigenvector of A. So why am I showing it here is because I want you to know that whenever you calculate the eigenvector, always normalize it. That means always divide it by its magnitude so that the norm, the modulus, whatever you call it, of the vector becomes 1. Here the n should be a unit vector. The n should be a unit vector. So if you get some c times n as your eigenvector after calculation, you have to normalize it and you need to use the normalized value for subsequent calculations. I hope I have made myself clear here. So the normal component of traction, it will be given by sigma into n, and that is equal to lambda times n. So what does this mean? The to find the normal component of traction. So this was just the traction, not normal component. The traction on a plane with normal n. This is a traction on a plane with normal n. So the normal component will be sigma nn, which is Tn dot n. And what we get is normal component of the traction is lambda. Now, what are the properties of principal planes at a point? Anybody has any doubt till now? So what are the properties of principal planes at a point? By definition, principal planes are the planes on which normal component of traction is maximized or minimized. So a question arises is, how many of such planes exist at any point in the body? So the answer is, a stress matrix is a 3 cross 3 matrix, and it will usually have 3 eigenvalues and eigenvectors, but they may not be all real. But there is some property of a stress matrix which I'd like to mention here. That is, stress matrix is symmetric. So this ensures that the eigenvalues and eigenvectors are real. Any 3 cross 3 matrix will not have all real eigenvector or all real eigenvalues. It is not essential that they will have it. But if a 3 cross 3 matrix or any n cross n matrix is symmetric, any n cross n matrix, if it is symmetric, this means that their eigenvectors and eigenvalues are real. And another corollary of a matrix being symmetric is that the eigenvectors corresponding to different eigenvalues, they are perpendicular to each other too. So suppose if I find the eigenvectors of a matrix A, and I know that the matrix A is symmetric, then I can say that their eigenvalues will be, the eigenvalues of A will be real. And then if all these eigenvectors are different, all these eigenvalues are different. Suppose we have lambda 1, lambda 2, lambda 3, and they are different, they are not equal. Then whatever eigenvector I find, x1, x2, x3, they will be perpendicular to each other. We can prove that here. So suppose we have found the eigenvectors of sigma matrix and the eigenvalues of sigma matrix, and the eigenvalues are lambda 1, lambda 2, lambda 3. Here I have like the proof for 2 of the eigenvectors have been shown. The similar steps can be followed to prove that n1 is perpendicular to n3 and n2 is perpendicular to n3. It can be for users. The same steps will be used. So from our eigenvector problem, what we have sigma into n equal to lambda n. So for eigenvalue corresponding to lambda 1, let's say our eigenvector is n1. So sigma n1 equal to lambda 1 n1. Similarly, sigma n2 equal to lambda 2 n2. Now what we do? We do a dot product of n2 in first equation. So sigma n1 dot n2 will be equal to lambda 1 n1 dot n. In equation 2, we will do a dot product of eigenvector n1. So sigma n2 dot n1 equal to lambda 2 n2 dot n1. Now these dot product, we know that n1 dot n2 equal to n2 dot n1. So it can be like they are the same essentially. These dot products are same. So another thing is here, if I want this sigma to come here, what will happen? We will get n2 dot sigma transpose n1 equal to lambda 2 n2 dot n1. We know one thing about sigma matrix from angular momentum balance, that it is symmetric. So sigma will be equal to sigma transpose. So this expression will become sigma n1 dot n2 equal to lambda 2 n2 dot n1. Now if I take a difference of this equation and this equation, I will get lambda 1 minus lambda 2 into n1 dot n2 equal to 0. Now what we have already assumed is that lambda 1 and lambda 2, they are not equal, they are distinct. So the only way this equation will be 0 is if n1 dot n2 is 0. And what do we know if if a dot b is 0? That means that a and b are perpendicular to each other. So that's why n1 and n2, they are orthogonal to each other, perpendicular to each other. Now the other thing is, suppose if there is a possibility that two of the eigenvalues, they are same. Suppose if I calculate the eigenvalue of matrices of stress matrix, and it comes out as, for a particular stress matrix, let us we get 2, 2, and 4. So two of the eigenvalues are same, they are equal. So what to do in that case? In that case, the third eigenvector, we can write it as the combination of two eigenvectors we already have. So what I will do, I will find the eigenvector corresponding to lambda equal to 2. I will find the eigenvector corresponding to lambda equal to 4. And I will do a linear combination of those to find the third eigenvector. So this means that if two of the eigenvalues repeat, there will exist an infinite number of eigenvectors. And they all will be in the plane formed by n1, n2. And all the planes which contain those eigenvectors, which has those eigenvectors as their normal, they will be principal planes. They will have the same eigenvalues. Those planes will have same eigenvalues or same principal stress component. Now, how do we represent the stress tensor or matrix? How do we write the matrix representation of stress tensor in principal plane coordinate system? So if you remember this figure, this was this is with us since week 1. Here the stress components on different planes of the cuboid or cube have been shown. Now, if it was the case of principal stress, principal plane, the normal components will be present and all the shear components will be 0. So to represent a stress, to represent a stress tensor, to represent the matrix form of a stress tensor in principal plane coordinates, we will get a diagonal matrix. And the components in the diagonal matrix will be the eigenvalues of the eigenvalue problem we have just solved. I hope this is clear to everyone. Now in lecture 8, we have already seen that how to maximize the normal component of the stress matrix representation or normal component of traction on an arbitrary plane. One thing I forgot to mention is that the off diagonal elements will be 0 in principal planes. I think I mentioned it. So the off diagonal elements will be 0. This means that shear stress will be 0 when stress matrix is represented in principal plane coordinate system. So how do we find the shear component of traction vector? We know the normal component of a traction vector on any arbitrary plane, T dot n. I'd like to mention one thing here because we have just covered the principal planes. There we had to find a plane where the normal component of the where the normal component of the traction vector was maximum or minimum. There we were using N1, N2, N3. Now in this part, in that was to find a plane where the normal components were maximum or minimum. Now we are planning to maximize shear component. So here also we will write N1, N2, N3, but these are not N1, N2, N3 of principal planes. Now from now on, we are discussing a completely different topic. So because there was very less time between the transition, I wanted to mention this. Now we are planning to find a plane where our shear stress component will be maximum or the shear component of traction will be maximum. So for mathematical formulation, we are writing N1, N2, N3, but those are not the N1, N2, N3 of principal planes. They are just N1, N2, N3. And when we find those, we will be able to find the planes where shear stress component will be maximum or shear component of traction on an arbitrary plane will be maximum. So we know that the total traction we know that suppose this is a plane with normal n. We know that the traction T, it could be in any other direction. It should not be aligned with n. So T is not necessarily in the direction of n. So what does this mean? This means that this will have some component along this side. So I will write it here. So ES hat is the direction of shear. So it is the resultant direction actually. So generally we deal with E1, E2, E3 coordinate system. Suppose uh, if our normal this n is in this direction, this is our normal. So there could be two different shear things, right? So their resultant I'm writing here as TS or tau, like sir has mentioned the rotation as tau. So if I want to write our traction T, what will it be? It will be the normal component of traction plus tau into ES hat. One thing to remember is that the ES hat, it is perpendicular to this normal. ES hat will be in plane, in the plane, in the plane of for which we are looking, of which in the plane which has normal n. Suppose this is the plane whose normal is n. So ES will be in plane. This is in plane. So from here, what can I write? If I take the modulus of T, it will be Tn square plus tau square. So we can write tau square as that is what has been written here. Then we replace T by sigma n and we replace the Tn by the value sigma n dot n. That has been written here. Now for simplicity, if we consider that the matrix representation of stress which we have been given, if that has been given with respect to principal stress, like principal planes, like we know the direction. We have written this stress matrix in principal plane coordinate system. So what we will have, stress tensor will be the diagonal matrix. It will be a diagonal matrix. And when you replace the stress tensor in the equation above, finally you will get this equation for tau. So this is the formula for the square of magnitude of tau on an arbitrary plane. One thing to remember is that shear will be acting in a direction on the plane given by vector sum of both shear components on that plane, which I was mentioning. This shear will be, suppose if our normal vector was even, let us assume, I will just, for, for example, I will show you. Suppose if our normal vector is, suppose our normal vector is E3. And this is the plane we are considering. Let us assume this is the plane we are considering. This is E3 is our normal vector. So Tn will be in this direction. This is the normal component of Tn E3 hat. This is the normal component of the traction vector. Now we will have something. This will be what? Tau 13. Here it will be tau 23. In the direction of E2, acting on plane which has a normal E3. That's why it is tau 23. Tau 13 because it is acting in the direction of E1 hat and it is acting on a plane which has a normal E3 hat. That's why tau 13. So this tau is actually the resultant, this thing. And this is the direction of this vector is ES hat, which I was mentioning there, ES hat. ES hat is the direction. This is the direction of this vector. So this will be ES. This is tau 13. So the resultant of tau 23 and tau 13 is our actual shear stress vector, or the shear component of the traction vector. Thus, the magnitude can also be written as tau 231 is 21 square plus tau 31 square, depending upon different planes. So if we had considered even plane, these would have been tau 21 and tau 31, and the total magnitude will be tau 21 square plus tau 31 square. Now, in a similar fashion, what we did for maximizing the normal component of the traction vector, we will find our augmented function again. So our original objective function is this thing. This is our original objective function. We have the same constraint of normal, that the norm of normal, it will be 1. Here alpha is the Lagrange multiplier. We have already used the lambda for principal stress, so that's why we have introduced alpha here. So if you write the objective function in initial notation, you will get this. lambda I square n I square summation over I, so on. So what we will do, we will follow the same steps. We will differentiate this v, our augmented function, with respect to the four variables n1, n2, n3, and alpha. And we will get these four equations. The three of them has been written here. Now, from these three equations, we can do one thing. We can, if I do n1 equal to 0, n2 equal to 0, and n3 equal to 0, what I will get a vector whose all the components are 0. So this is a trivial solution. This is not a solution which we are looking for, or which has any importance. Other things what can be done is, like, we can make one of these 0. Like suppose if I make n1 equal to 0, what will happen? This term will not vanish. This term will be there, but n1 is 0. So the overall, this expression will become 0. So now when I fixed n1 equal to 0, I have two different equations. And there I cannot do n2 equal to 0 and n3 equal to 0. What I will do there, I will do the term in the bracket that will be 0. So what I will get this expression equal to 0. I will get lambda 3 square minus 2 summation lambda ni square lambda 3 plus alpha equal to 0. Now I can solve these two equations because these are the linear equations in terms of lambda. Sorry, in terms of alpha. So first, what I can do, I can take a difference of these two equations. When I take the difference, it will be lambda 2 square minus lambda 3 square minus 2 times lambda 2 minus lambda 3, and that will be multiplied by this term. So this is the expression we will get. We can take lambda 2 minus lambda 3 out. And finally, we will get this equation. Now, lambda 2 and lambda 3, they are distinct. Like it was assumed that we are taking the principal stress coordinate system. So in that case, or the principal planes coordinate system, so there the lambdas, the eigenvalues, they are distinct. And suppose if they are equal, then we cannot directly write it as 0. So here it has been written that we can cancel lambda 2 minus lambda 3. This has been done assuming that lambda 2 and lambda 3 are not equal. So from there, we will be able to find the values of n1 and n2. Now, you can see the equation 14 is lambda 2 1 minus 2 n2 square plus lambda 3 1 minus 2 n3 square. If we are assuming that for any arbitrary lambda 2 and lambda 3, this thing is true, the only way it is possible is if I force this part as 0, 1 minus 2 n2 square as 0, and 1 minus 2 n3 square as 0. Then only for any lambda 2 or any lambda 3, this expression is true. So this will give us the value of n2 and n3. We already assumed that n1 equal to 0, so we will get four different sets of solution. It will be 0, 1 by root 2, minus 1 by root 2, 0, 1 by root 2, 1 by root 2, 0, minus 1 by root 2, minus 1 by root 2, and 0, minus 1 by root 2, plus 1 by root 2. Now suppose if we follow the same exercise by forcing n2 equal to 0, then we will have to solve the expressions for n1 and n3. If we force n3 equal to 0, then we will need to solve the expressions which correspond to n1 and n2. So overall, for each case, we will have 4 sets of solutions. So overall, we will have 12 sets of solutions. Now, how do we find the magnitude of traction components on plane having maximum C? So we already know the values of n1, n2, n3 now. And we know the maximum shear of this. We can plug those values here. And when we do that, we'll find that the magnitude of the maximum magnitude of maximum shear is lambda 1 minus lambda 2 by 2. If we are thinking that n3 equal to 0. And the value of sigma nn it will be lambda 1 plus lambda 2 by 2. Now, don't you think this is slightly different from what we read when we were reading principal planes? There, for maximum value of sigma nn, like the plane which had the maximum value of normal component of stress, the shear stress was 0. But for this case, where a plane which has the maximum value of the shear stress, for that, the normal component of stress is not 0. Students make a lot of mistake here. They Students make a lot of mistake here. What they will do, they will assume that, okay, so the shear is maximum. They will get confused with the principal planes concept and they will write the normal component as 0. But that is not true. Keep this in mind. Suppose if we had done n1 equal to 0, so we had got this expression. And if we had done n2 equal to 0, we had got this expression. Now this has like till now we have recapitulated till lecture 8. Now we will move on to Mohr circle part. For Mohr circle, there is one requirement that the plane which we are on which we want to find the stress components. It should be perpendicular to at least one of the principal planes. Suppose if we are assuming that our stress tensor like matrix is represented in a coordinate system which is perpendicular to E3, like the third principal plane. So we will get a matrix like this. The top diagonal terms related to 3, like tau 3 1, tau 2 3 2, this will be 0. Also, the normal vector will look like this. The normal vector of plane on which we want to find the stress matrix representation. This will look like, because we are assuming the plane is perpendicular, the plane on which we find to plane on which we want to find sigma is perpendicular to root 3. That's why this is happening. The same reason follows for this sigma. This is the final representation of sigma. Of course, the matrix representation of sigma in new plane, which we will look at. So in class, sir has already derived the formulas for the transformation of a stress. Like if you're, so this example sir took was about E3, the rotation was made, and this was the plane. And this is the normal vector of that plane. This is making an angle alpha with E1. This is our E2. So I will draw this again here. So this is our new plane on which we want to find, like we want to know how will the stress matrix look. This is the normal of that plane. It is making an angle alpha with E1. By convention, the shear stress will be in the 90-degree clockwise direction, counterclockwise direction of normal. So the shear stress will be what? This will be the direction of shear stress on that plane. This is tau. This will be what? This is T and the normal component or sigma n. Should write sigma. This is the direction of sigma n and this is the direction of tau, the shear stress. Tau is shear stress. So n is what? N is cos alpha, sin alpha. See. You can see what I said earlier. The third part will be 0. We can see that here also. Because n doesn't have any component in E3 direction. And what is the direction of this shear stress? This is n perpendicular, right? We can write the direction of shear stress as n perpendicular. Or what I earlier mentioned was ES hat. Like these are the same things. In my notation, I wrote ES hat, but sir has followed n perpendicular in his lectures. So I'm writing it here also. This is the same. I wrote spins. This is n perpendicular. So what will be n perpendicular? This will be minus sine alpha, cos alpha, and 0. You can also try to calculate these yourselves. You can use the rotation formula or you can use the geometry, whichever way you want. Try it that. Try and check that if you are getting the same results which I have shown here. Now, if we go by formula, what will be our normal component like sigma n? This will be, suppose we are given a sigma. Sigma has been given in E1, E3, E2, E3 coordinate system. We are given in this. So I will write our objectives clearly here so that you don't get confused. We have been given sigma. Let us say in XYZ coordinates. X, Y, Z. Now we want to find representation of sigma in a coordinate system, in a new coordinate system. Which we So we already know a matrix representation of sigma in some coordinate system x, y, z, or we can say E1, E2, E3, whatever you like. It's up to you. We now need to find what will be the representation of this sigma in a new coordinate system, which we will get after we rotate E1 hat, E2 hat plane by an angle alpha in counterclockwise direction. This is important. The direction is important. You will get to know about it later. About E3. So what are the formulas which we have found? We have found that the new sigma will be what? Sigma normal will be. If you follow the lecture sir has already taken, you will get. I'm just writing the formulas here so that we can move on to numerics. And today I will show you a small code also. I know that in this course, the coding is not required and it is like not a mandatory thing, but I've seen many mechanical engineers, they are very afraid of coding. So I will just show you a simple code that whatever we have read till now, how to implement that in a MATLAB. It will be I think I will take maximum 15 minutes at the end so that you get a hang of like how to code these things or how a computer can help you to solve these things. So first I will like solve some numerical problems, maybe after 5 to 10 minutes, and then we will move on to coding. I've already written it and let's see how does that go. So sigma n will be what? If we follow the formula, the sigma n will be sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cos 2 alpha plus tau xy sin 2 alpha. Now, if you have a question like why sigma 33 is not coming or sigma zz it is not coming in this expression, the reason is we have assumed that sigma 33 is out of plane. And this sigma n, whichever we are finding, it is again in the plane only. So its contribution will not come. You can try like for a generic thing, like you can assume that the you can assume a new coordinate system where you are not just rotating about sigma E3. There's some complex kind of thing. If you go by the formula like sigma nn equal to sigma times n dot n. Try this at your home and you will see that there will be some other like sigma zz will be there. But in this case, since we are assuming that sigma zz is only present in E3 plane and it is like in the normal direction of E3, it will not have a component in stress components of a in-plane thing like of XY plane. So just try it at your home. You try to take a general sigma matrix, try to take a general normal. In our case, the normal has third component as 0. E3 component of normal is 0. Try to take a normal where that is not 0 and just try to look at it. Like maybe try to derive it. You will see that sigma 33 or sigma zz component will be present in the expression. But in your course, I think that is not required. That is something which extra you can do. Now, what will be the shear stress component of on that plane? The expression is sigma xx minus sigma yy by 2 sine 2 alpha plus tau xy cos 2 alpha. So this was the formula which was derived. Now moving on to Mohr circle. We want to represent this in a circle. So the first step was that we defined the radius of the circle by sigma xx minus sigma yy by 2 square plus tau xy square. So how did it come? So it was like we assumed that there is a right angle triangle and one of the angles of the right angle triangle is 2 phi. Base for this right angle triangle is sigma xx minus sigma yy by 2 and the height is tau xy. Okay. So from here we can also see one thing, that tan 2 phi, it will be what? It is tau xy by sigma xx minus sigma yy by 2. This gives us 2 into tau xy by sigma xx minus sigma y. Finding this angle 2 phi is important. You will see it later. And similarly, we can find cos 2 phi and sin 2 phi. So cos 2 phi will be sigma xx minus sigma yy by 2 times r. This hypotenuse, it is r. Sin 2 phi is tau xy by r. So if we want to write the above mentioned sigma nn and tau, sigma nn and tau in terms of this r and phi, what we will get, I'm writing the final expression here. We will get sigma equal to, or sigma is sigma nn basically, equal to sigma xx plus sigma yy by 2 plus r into cos 2 phi minus 2 alpha. Tau is what? R into sine 2 phi minus 2 alpha. So the above steps which we have done, it has basically simplified the way our equations will look. Though we need to calculate this radius r and this angle phi, but this expression, it becomes like quite simpler to use. By using the above formula, we can easily find this r and 2 phi, and you can replace it here. And this alpha, you know the value of this alpha because it will be given in the question that we are rotating the XY plane or YZ plane or whatever plane we are rotating by some angle. So we know this alpha. What will this be? This we know from the problem. This we know from the problem. What about R and phi? We calculate it. We calculate it because by using this stress matrix we have been given, by using the matrix representation of stress, representation of stress, we have been given. Now, if you look at this expression, and I hope you have read this in class 11th or 12th, this expression actually represents a circle. Maybe I will just slightly modify it and it will, maybe you will be able to visualize it. Sigma minus sigma xx plus sigma yy by 2 equal to r cos 2 phi minus 2 alpha. Tau minus 0 equal to r sine 2 phi minus 2 alpha. So if we do these squares on both the sides and add, what we will have sigma minus sigma xx plus sigma yy by 2 whole square plus tau minus 0 whole square equal to r square. This is the equation of circle which has center at sigma xx plus sigma yy by 2 and 0. This is our tau plane, sigma tau plane. We know sigma y, we know sigma xx. So somewhere here we have sigma xx plus sigma yy by. This is the center. If we write in the coordinate system form, it is because we have to show that tau is 0, so it's better to write like that. Suppose we also know the value of tau for suppose if I want to find what is where is our even plane, we had to find it, right? Because the angle alpha, if you remember, we know that the angle alpha is with respect to even plane. Let's say if this is our even axis or even axis, sorry. So this is alpha. So we need to find the point where we have even axis, and this is alpha. So we know tau xy and we know sigma xx. So what we will do, we will find the point of intersection. This is the point of intersection. So this is what? This is tau xy. The height is tau xy. This is r. This is 2 phi. So we now know the radius of the circle. We know the center of the circle. So we can easily draw our circle here. This is our circle. This was our center. Much better now. This will be tau max. The value of the shear stress at the center of the circle will be the maximum shear stress which will be present. And this will be equal to λ1 minus λ2. So we'll take a 5 minutes of break now. And after that, we shall continue. So let's solve some problems and then we'll move on to the coding part. So suppose we have been given a stress matrix. And someone asks you, find normal components. Find the magnitudes of normal and shear components along E1, E2, E3 directions. One thing could be that one follows the usual step. The usual step is first find the traction by this formula. N will be what? E1, E2, E3. Then you will do normal component magnitude will be T dot N. So basically you will be having sigma N dot. To find the shear component, what one can do? Tau will be what? Square root of tau is what? Square root of so you can use this formula also. But if you look at this problem and if you realize that this has been given in E1, E2, E3 coordinate system only, and what they are asking for what will be the normal component of along normal component of traction on E1 plane, normal component of traction on E2 plane, and normal component of traction on E3 plane. You realize that the diagonal elements, like for E1 plane, the first element, for E2 plane, the second element, and for E3 plane, the third element. These are the normal components of traction on E1, E2, and E3 plane respectively. So the answer is on E1. Tn is what? 5. And what will be tau? It will be tau 21 square plus tau 31 square. First of all, I will have to look at one thing. We have to make this matrix symmetric. I thought somebody will intervene, but nobody did. It did this intentionally, actually. So what is tau? The answer is it will be tau 21 is what? 4 square plus 6 square. Root over 16 plus 36 square root 52. On E2 plane. So when I say even plane, E2 plane, that means that a plane whose normal is even. This means that even plane. A plane whose normal is E2, I will say it as E2 plane. So keep that in mind whenever I say that. So for E2 plane, what will be the normal component? The answer is 8. And what is the shear component? The answer will be tau 12 square plus tau 32 square. 4 square plus 10 square. Root over 116. On E3 plane, what is the value of normal traction? The value is 45. And what is the value of shear stress? It is tau 1 3 square plus tau 2 3 square. This will be what? 6 square plus 10 square, square root of 136. So this was one of the questions. Now another question which can be asked from this in competitive exams also is like find the maximum value of stress on a plane, find the minimum value of stress on a plane, or find the difference of the maximum and minimum values of stress on a plane, or find the maximum shear stress which can occur on the body. So let's do a problem about that. Maybe first let's take this. So suppose we are given sigma equal to 1, maybe let's take 7, 9. So here it will be 7, here it will be 9 by default. It should be now 4. Let's take 10 here. So we will have 10 here. And this is something, let's take it as 0. I hope the determinant of this matrix is not 0. Let me check it. So let me check it once if the determinant is coming 0 or not. Not, then we will solve it. Now MATLAB is a proprietary software, so I don't know if you will be having access to this or not, but when I will teach you coding, I will tell you some things at that moment. Just look at, just let me check this one, 179,410. So our matrix in this, let me check if the determinant is. So it's not 0, so it's a good thing. Anyways, so the question can be what? Find the principal values of stresses. I'm just giving you the all the variants of question that can be asked from the principal stress question. Find the maximum, principal values of stresses. Another question can be find the difference of maximum and minimum. Difference of maximum and minimum value of stresses. Minimum value of stresses. Sorry, principal stresses. Other question can be find the maximum value of shear stresses. Find the maximum value of sigma. Oh, sorry. Oh, so sorry. Not maximum value of sigma. Find the values of sigma and the normal component of stresses on planes where shear stresses are maximum. Okay. So how will you deal with these problems? All of these problems will have the similar way to attack. First step is step 1. Find the eigenvalues. Find the eigenvalues of sigma. How will we do that? You do it by sigma minus lambda I, determinant is 0. You do this thing. So basically we have 1 minus lambda 7. Seven, 9, 10. To take its determinant and equate it to 0. So you will get a polynomial from here. Solve that polynomial. Because this was a 3 cross 3 matrix, so you are getting a cubic polynomial. Actually, you will get a cubic polynomial. I want to be specific here. Solve that polynomial and you will get lambda 1, lambda 2, lambda 3. Now the convention which is being followed in this class by Professor Ajit Kumar is that we are assuming that lambda 1 is greater than lambda 2 and lambda 2 is greater than lambda 3. So write in that order. When you write the answer, write in that order. So I will write the answers of this question. Let us say this is A, this is B, this is C, this is D. Okay. So what will be A? Maybe I will just give you the values also. So A will be 19.1129. So answer A is lambda 1 equal to 19.1129. Lambda 2 is what? And this was a very good question, I think, because we got negative values also. So I don't have to take another matrix to show you some things. So in these two, minus 4.5 will be greater than minus 9.5. So lambda 2 should be minus 4.596. Do not make a mistake that the magnitude, make a mistake that the stress with more magnitude will be larger than the other one. No, you have to consider the sign also. In my BTech, I saw my friends making this mistake. So lambda 2 is minus 4.95960 and lambda 3 is minus 9.5169 or 9669. You won't be having the facility of finding the eigenvalues using MATLAB in your exam. So I just wanted to show you these steps. That's why I have shown it here. Now the part A is find the principal values of stresses. So the answer is lambda 1 will be 19.1129. Lambda 2 is minus 4.596 and lambda 3 is minus 9.5169. Part B is find the difference of maximum and minimum value of principal stresses. So in part B, you will do lambda 1 minus lambda 3. It should be plus, right? 6 to 8. Suppose if the unit of this stress was in megapascal, they have given in megapascal. So these lambda 1, lambda 2, lambda 3 will also be in MPa. I should write the units here because in exam they will come with units. Find the maximum value of shear stresses. So here you remember there were three cases if we are considering n where we are considering that even component of n was 0. So if it was 0, some n2 and n3, then the shear stress will be lambda 2 minus lambda 3. So I should write say tau max. Tau max is what? Lambda 2 minus lambda 3 by 2. And so we will write it as minus 4.596 plus, oh, sorry, not plus, minus 9.5169. So the answer is 2.640. Suppose if normal was such that its component in E2 direction is 0. tau max will be if n was in such that the n3 component was 0. So tau max will be what? Lambda 1 minus lambda 2 by 2 modulus. This is 19.1129 minus 4.596 by 2. For fourth part, where we have to find the, suppose if I write it as, okay, for fourth part also we will have three cases. For first case, when n1 equal to 0, there sigma n will be what? Lambda 2 plus lambda 3 by 2. Okay. Here you can write sigma n as lambda 1 plus lambda 3 by 2. And in this case, give me 1 minute, I just like to recheck one. Yeah, that's right. And when n3 is 0, you will write sigma n as lambda 2 plus, sorry, lambda 1 plus lambda 2 by. So the main motive I did this question in this one go was to show you that what are the different variants of the same question. One other variant could be they can ask you find the values of shear stress, or they may even write shear component of traction vector, whatever the wording is, on principal planes. Principal planes. So for E part, what you can do, you can follow the already told procedure, or you can be clever and directly say since. So this symbol is for since. I hope you remember this. Since on principal planes, shear stresses are 0. Shear stresses are 0. stresses are 0, hence tau equal to 0 on all tau ij will be 0 on all principal planes. This will save you a lot of time. You can try to follow the similar process like the uh, whatever the normal procedure is, you will get the same result. So just you can write this also. The reason I wanted to do all 5 variants here is to show you that though on principal plane, where the normal components of the stresses have a maxima value or their maximum, and there the shear stress is 0. All the shear stresses are 0. But the opposite is not true. On planes where the shear stresses are maximum, there the sigma nn are not 0. Maybe we can do some objective questions also. Let me open some of the questions. So these were the questions which have been asked by you, asked from you in the weekly assignment. So I will not be like dealing with these questions. I will try to like answer other questions. Which of the following is true with respect to principal planes of stress tensor? There are planes on which normal component of traction is maximized only. There are planes on which normal component of traction is either maximized or minimized. They are planes on which normal component of traction is minimized only. And the fourth option is all planes are principal planes. So the answer will be B. Answer is B. On principal planes, we get the maximum as well as minimum value of normal stresses. The principal stress components are given by the option A is eigenvalues of the stress tensor. Option B is eigenvectors of the stress tensor, and option C is diagonal components of a general stress matrix. So the answer A will be true. The principal stress components are the eigenvalues of the stress tensors, and which we have already found also in the last example I showed you. State whether true or false. All principal stress components are always greater than sigma xx. Sigma xx represents the normal component of traction on a plane with normal along x-axis. This is false. Suppose if this xyz coordinate is not principal stress axis, suppose if this is some orbit axis, so you will have to first find the values of like principal stresses. You will have to first find the eigenvalues, and then only you can say comment on this if the sigma xx is greater than the principal stress component or not. We cannot directly say that sigma xx will always be greater than the principal stress component. So this statement is false. 9. A stress matrix has real eigenvalues, can have real or imaginary eigenvalues. Eigenvectors are perpendicular to each other. Eigenvectors are parallel to each other. So the answer will be real eigenvalues. The reason stress matrix has real eigenvalues is because it is symmetric and the entries of the stress matrix are real. That's why we get real eigenvalues. And this is also true. Eigenvectors are perpendicular to each other. Eigenvectors are perpendicular to each other if we have distinct eigenvalues. If we don't have distinct eigenvalues, there I have already told you how to find the eigenvectors. But this was for a generic stress matrix, so option A and C will be correct. Suppose that two of the eigenvalues of stress tensor at a point become the same. How many principal planes will exist in this situation? The answer is infinity, because we have infinite eigenvectors. So whatever plane will have that eigenvector, it will be a principal plane. Given below is a stress matrix, what will be the difference of between the largest and smallest principal stress component? So I've already solved one of the problems, and you can follow the same pattern and you will be able to find this, like how to solve this one. So lecture 7 answers are given here. Now we move on to lecture 8. Question 1 and 2. Okay. The normal component of traction on planes where shear component is maximized. The options are must be 0, is usually non-zero, must be non-zero and equal to magnitude of shear component, and none of this. So the answer will be B. It can be 0. There may be a case where sigma n becomes 0, but usually it is non-zero. We have already solved this in the last question also. So the answer is 3B, non-zero, usually non-zero. Now let's move on to the problems of the Mohr circle. So the question is a point on Mohr circle which is at an angle theta clockwise from the point corresponding to even plane will correspond to. Okay. So for Mohr circle, remember one thing. For Mohr circle, if the point was, if the angle was alpha and counterclockwise, I will write counterclockwise as CCW. Okay. So on Mohr circle, we will find it for area. Yeah, let's. I will open it and paint. Okay, so if it is given on Mohr circle, angle is if it is given that a plane is found by rotating our existing plane by angle alpha with respect to E3, the angle between plane normal and our E1 axis is alpha, then and it is the rotation is counterclockwise. Then on Mohr circle, suppose if this was the point for E1, like if here it is E1, like this is the point for E1. So we will have to move clockwise by angle 2 alpha. So from E1 hat, we will have to move clockwise by angle 2 alpha. So remember this. The angle on Mohr circle, we will have to move in the opposite direction with twice the magnitude. This is 2 alpha. Now in the question they are asking for the clockwise case. So on Mohr circle, what will happen? Suppose if this is E1. So we will have to move counterclockwise by angle 2 alpha. So this is what we will have to do. You can see this from the expression also. In this expression, this 2 alpha is there, right? And you can see it is lagging. It is coming with minus sign. Now, if we move clockwise, then what happens in clockwise? Alpha will come with negative value. Let us assume alpha, we can replace it by minus theta. So this will become r cos 2 phi plus 2 theta. So you can see from the expressions also that is true. But for exam purposes, you can just remember this, that you will have to move twice the angle in opposite direction on Mohr circle. So the answer will be A. Suppose we are given the radius of Mohr circle, which of the following can we find using that information? Okay. We can find the maximum shear stress because that will be equal to the radius of the Mohr circle. To find the principal stress components, you will need other values like sigma x, sigma y also. But to find the shear component of traction, maximum shear component of traction, tau max, we can directly equate it by radius r. And if you want, you can look at here also at the expression. You can have a look at the expression. So the expression for tau is r sine 2 phi minus 2 alpha. So the tau max will be when radius is equal to tau. That means when 2 phi minus 2 phi 2 alpha becomes pi by 2. At that time tau will become equal to r. And that will be the maximum value of shear stress you will be having. At a point inside a fluid body, so if the fluid is static, then all three are true. Every plane in the is a principal plane because in a static fluid, you always have the normal component of the stress, that is the pressure. If you remember, for static fluid, sigma was minus pi. So in that case, every plane will be a principal plane. All principal stress component will be equal, and Mohr circle will reduce to a point because all the principal stresses are equal. I want you to do one exercise. You write sigma as minus p 0 0 0 minus p 0 and 0 0 minus p, and try to find the eigenvalues of that. You will realize what I meant here, and try to draw the eigenvalues which you have found. Try to draw it on Mohr circle. But this will be true for a static fluid, like when there is a condition of static fluid. So I'm assuming the static condition here. If the fluid is moving, their shear component will come into picture. So the assumption is that the fluid is static. So answer will be all of it, A, B, C. Now question number 9. See if it is allowed or not. Okay, it's allowed. So the answer will be A and D. How do I know that? You will have to go and check the lecture between 4 to 5 minutes. The lecture sir has taken. There he mentions this. The plane which we are looking at should be perpendicular to at least one of the principal axes. So that is true only in this case, 9A and 9D. So these two are the correct options. Now question number 10 is the following state of stress exists at a point. So they have given you a sigma and they are asking from you that what is the value of principal stress. So in this question, first look that, okay, the stress matrix is given such that the plane 3, the third plane, is like the coordinate system is actually perpendicular to the third plane. So the third sigma 3, like one of the sigmas will be 10. So you are sure of that. Now usually how do you find the values of principal stresses? Follow the same method and you will be able to find this. I leave the other questions to you. You can solve them by yourselves. Now I'd like to discuss the code which I was mentioning. So suppose we have a sigma matrix. So how many components in a sigma matrix are independent? After applying A and B, only 6 components are independent. MATLAB, what I did, SN1 means sigma 1 1, like the normal component, first normal. SN2 is sigma 2 2, and SN3 is sigma 3 3. SXY is sigma 1 2. SXZ is sigma 1 3, and SYZ is sigma 2 3. So first I defined all the values, like for example, in this case, it is 0 0 0. All the diagonal elements are 0. And only we have SXY, like the sigma 1 2 is 100. So if we go here, the first part is sigma 1 2 is 100 and other things are 0. All these are 0. So these two are non-zero. So the sigma matrix is what? Maybe I will run the code and I will show you there only. It's better to do that. So this is my stress matrix. Now, what am I doing here? Suppose if somebody told me that find what will be the normal component of this stress matrix in E1 direction or E2 direction or E3 direction. So it will be just the, like for E1 it will be sigma 1 1, for E2 it will be 0, sorry, sigma 2 2, and for E3 it will be sigma 3 3. So this line is basically accessing this matrix, like this matrix, the first and 1 comma 1 coordinate is getting accessed and getting assigned to SXX. SYY is what? 2 comma 2. So this SN2, 3 3. SZZ is what? This last component. Now you see here, SHE1 is what? The total shear component on E1 plane. SHE2 is the total shear component on E2 plane. SHE3 is total shear component on E3 plane. So let's look at the like shear component of total shear component on E1 plane. What was it? Sigma 1 2 square plus sigma 2 1 square plus sigma 3 1 square. So since the stress matrix is symmetric, we can write it as sigma 1 2 square as plus sigma 1 3 square. So that is what has been written here. SQRT function is what? Square root sigma 2 1. I am accessing the second component, like the first component of second row. This is XXY plus sigma 3 1. I'm accessing the first component of third row, first column and third row. That is written here. So what we had to do is square root sigma 2 1 square plus sigma 3 1 square. So that has been coded here. So if I move forward, you can see that it's coming to 100. Let's calculate that manually also. So tau will be what? Root over 100 square plus 0 square, because sigma 1 2 is 100 and sigma 1 3 is 0. So it is 100. So you can see I'm getting the same result from the code. And the same thing is followed for SHE2 and SHE3. Now you can see this step. I told you that you have to find the eigenvector as well as the eigenvalues, right? So this command in MATLAB, eigstray, here I have written the name of my matrix. I have written it as stray here, right? So I'm calling this eig function on this matrix as input. So stray is the input for eig function. What it will do, it will give me the eigenvector as well as the eigenvalue of this stress matrix. So let's run the code and see what we get. So D, let's see what is D. So D is the matrix which stores the eigenvalue, like the diagonal elements of this D are the eigenvalues. So for this problem, the eigenvalues, if we calculate manually also, from code we are getting lambda 1 is 100, lambda 2 as 0, and lambda 3 is minus 100. Let's try to solve it manually. 0 minus lambda, right? 0, right? 0 minus lambda, 0. So eigenvalue will be what? Suppose if it is A, so that A equal to 0. So minus lambda into lambda square minus 0 minus 100 into minus lambda into 100 equal to 0. This is what 100 square lambda minus lambda cube equal to 0. So lambda into lambda square minus 100 square. So what are we getting from here? One solution is lambda equal to 0. Other solution is lambda plus 100 equal to 0. And lambda minus 100 equal to 0. So lambda 1 is what? 100 from here. Lambda 2 is 0. Lambda 3 is minus 100. See, I'm getting the same result. Minus 100, 0, and 100. So in MATLAB, they actually order it like, depending upon the values. So D is basically the diagonal matrix formed using the eigenvalues of stress tensor. Now V is the eigenvector. So I leave this exercise to you, how like you have to manually find the eigenvector, and you will find that corresponding to lambda equal to minus 100. So this is minus 100. You are getting this first eigenvector minus 1 by root 2, 1 by root 2 and 0. Corresponding to lambda equal to 0, you are getting this 0, 0, 1. And corresponding to lambda equal to 100, you are getting 1 by root 2, 1 by root 2 and 0. So this is where I will end this session. I hope this was a fruitful session for you. If you have any doubt, you can ask me. Otherwise, I will end this session. Give me 1 minute. I forgot to put on this. So if any one of you has any doubt, you can ask me. You can unmute yourself. You can ask me or you can write in the chat. The last part was just to show you that like using codes also you can find different things. That will not be a part of your exam. That's why I showed you after 8 p.m. That was something extra for you. Okay, my email ID. Are you a part of this Google group? So have you joined this course on Swayam, like the NPTEL? You can unmute yourself, Kiran, if you want, if you have the option. Okay. So actually, I will show you one thing. I hope you have joined this course. So if you go to course, if you go to this course, there is an option ask a question. If you ask a question here, see this, I have replied here. So I will reply to you. So you can ask question directly there. And if you ask question there, then apart from me, Roshan or like professor himself, they can also answer your doubt. But this is my email ID. I will give it to you. Yeah, this is my email ID, but you can also post your like questions here. Ask a question, you will be like told by Google to join the Google group, and after joining the Google group, you can post your answer questions here and we will answer your question. If you personally mail me also, then also I will answer, don't put. So I've given you my mail. Is there any other doubt anyone has? Then They can ask, or I will like end this session. This is a different kind of question. So here the like, how should I say, you will have to calculate the octahedral stress. Okay, so they are asking for pressure, right? They are not asking for stress from you. They're asking what is the pressure, and pressure is what? It is compressive load. So that's why the answer is minus 200, I guess. I don't know from where are you bringing this question, but the octahedral stress will be 400 plus 100 plus 100 by 3. So that will be the value of sigma. But they are asking that what will be the pressure. So pressure will come with negative sign. Is there any other doubt? Anyone has any other doubt, then they can write or they can. Kiran, do you have any other doubt or should I end this session now? You were writing something, that's why I'm holding it. Otherwise, okay. Okay, then all of you, thanks for joining this session. I hope to meet you again next week on Tuesday from 6 to 8 p.m. Thanks and happy Independence Day again. Thank you. Bye bye.